All right, good morning, guys. Today we're going to be covering 8.7, inscribed and circumscribed polygons. This will be under Unit 8, circles. Now, this will be a pretty short lesson with a lot of definitions, so keep that in mind as we go through. Feel free to pause the video at any time if you need to, and review back through at any time as well. Let's go ahead and get started. First off, our first definition is of inscribed. A polygon is inscribed in a circle if all of the vertices lie on the circle itself. So, an easy way to remember this is inscribed is equal to inside. So if I have a polygon, and it doesn't matter what type of polygon it is, it could be a triangle, it could be a parallelogram, it could be a quadrilateral, it could be a pentagon. It can be any type of polygon possible. If it is inscribed in a circle, then all of its vertices will lie on the edge of the circle itself. So, I have a little example here. Within circle O, we have ABC. Triangle ABC is said to be inscribed within circle O. The next definition that we need is circumscribed. A polygon is circumscribed about a circle if each of its sides is tangent to the circle. So as we can see here, I have all these segments that are going around our circle, and each of these is only touching the circle at one point, making each of these segments a tangent segment. And if that's the case, then we would say that the circle is circumscribed inside polygon PQRST. So, an easy way to remember circumscribed is to relate it to circumference. Circumference is the distance around a circle. Circumscribed is segments lying around a circle. Of course, those are all tangent segments. Very important that they're tangent. But regardless, we can relate those two together. This brings us to the next definition, and that definition is of an incenter. Now, incenters are found within inscribed circles. So, let me go ahead and just put this up here real quick. Polygon PQRST is circumscribed about circle F. That's how we would write it. So, again, ABCD is inscribed in circle O, or circle O is circumscribed about quadrilateral ABCD. Again, these can be written either way. I can say that the circle is circumscribed about the polygon, or I can say that the polygon is inscribed about the circle. Both ways work. Our next definition is of circumcenter. And we've covered circumcenter in the past. It was when we were going through our construction unit. However, with circumcenters, I'm not going to be asking you to find the circumcenter. However, you will be asked questions like, given the circumcenter of the circle, find chord AB. So you'll see stuff like that down the road. But just know that if I have the center of my circle, and it is inscribed, and I have a polygon inscribed within the circle, then the center of the circle is said to be the circumcenter of the polygon. So if I have a circle around circumscribing a polygon, then I would say that the center of that circle is the circumcenter of that polygon. Again, circumcenter can be found when you're doing the circumference of the circle, or when you're circumscribed about the circle, about the quadrilateral or polygon, whatever it may be. So again, circumscribed, circumcenter, and circumference, all related to each other, and use those to connect between the three. The next definition that we have is of incenter. The center of a circle inscribed in a polygon, so again, I can see the circle is inscribed within the polygon. That center is the incenter of the polygon. So the incenter is found inside the inscribed circle. And very easy to remember incenter and relate that to everything else, because they all start with in. Incenter, inscribed, inside. All right. Next up, we have a couple theorems before we get started on our practice problems. Our first theorem deals with the angles of a of a quadrilateral that is circumscribed within a circle. So I see we have quadrilateral ABCD here, and it is inside the circle, so therefore the circle is surrounding it. If this is the case, if you have a polygon within your circle, then the opposite angles will always be supplementary. They'll add to be 180 degrees. So angle A is supplementary to angle C, and angle B is supplementary to angle D. And again, that happens anytime that I have a polygon inscribed within a circle. So very important, opposite angles will be supplementary if you have a polygon inscribed within a circle. All right, our last theorem before we actually do some sample problems. It states, if I have a parallelogram inscribed within a circle, so the parallelogram is inside the circle, the only shape that that parallelogram can be is a rectangle. There's no other choice. Now, of course, could it be a square? Yes, because a square is a rectangle. So those are the only two choices, rectangles or squares, because again, a square is a rectangle. So the best way that I can determine if we have a parallelogram is if I see opposite sides being parallel. And again, we've covered all the ways that you can determine if we have a parallelogram in the past. So if you see that we have a parallelogram, then the shape has no choice but to be at least a rectangle. Could it be a square? Absolutely. Now, as a result of that, BD and AC, those are both diameters. They both pass through the center of circle O. And of course, circle O is the center of the circle. And since O is the center of the circle, it creates a lot of radii for us. So we have 4 different radii that are shown in this picture. OA, OB, OC, and OD. Those are all of our radii. All right. With that being said, we've now covered all of those theorems, all of our definitions. Let's try out some practice problems. Here's our first sample problem of the day. We're given that arc PS is 110 degrees, arc PQ is 100 degrees, and we would like to find angle R and angle P. Now, first off, where are angle R and angle P at in relation to the circle? Are they on the circle, inside the circle, or outside the circle? Well, both angles R and P are on the circle itself, and what we need to remember is that if we have an inscribed angle, such as angle R, it will always equal half of the arc that it is facing. In this case, it'd be arc SPQ. And again, an easy way to see that is if I draw in my angle for angle R, I draw my 2 rays, I can see where it intersects the circle. So that intersected arc is that entire piece of where my angle cuts the arc at, that is. So as I can see in this problem, angle R is equal to half of arc SPQ, and arc SPQ is 110 degrees and 100 degrees. So therefore, I have the measure of angle R is equal to half of 110 plus 100, which is 210. Well, half of 210 will bring us to 105 degrees. So therefore, angle R is 105 degrees. Next, we're going to go ahead and solve for angle P. So for angle P, let me go ahead and focus now in on angle P instead. Angle P is also on the triangle. And if angle P is on the triangle, I can go ahead and draw these segments in, draw in my angle itself with the 2 rays, and we can see where it actually intersects the circle. That'd be arc QS. But we don't have arc QS. We can find it, however. There's 360 degrees in a full circle. We've already used 100 degrees and 110 degrees. All that would be left is arc QS. So therefore, I can do 360 degrees minus 210, because that's 100 plus 110. Well, 360 minus 210 will leave us with 150 degrees. Half of 150 degrees will leave us with angle P as 75 degrees. So therefore, P is 75 degrees, and R is 105 degrees. Is there another way for me to find angle P after I find angle R? Well, yes. It goes back to our previous theorem that we just talked about. If I have a quadrilateral inscribed within a circle, then opposite angles are supplementary. So therefore, angle P is equal to 180 degrees minus angle R. Well, angle R is 105 degrees. That just gives us 180 minus 105, which again will bring us right back to angle P equaling 75 degrees. So again, both ways work. It's up to you on which way you would prefer, but just know that you can use this method if you have a quadrilateral inscribed within a circle. All right, let's try out our next sample problem. In this sample problem, PQ is equal to 15, QR is equal to 20, RS is equal to 7, and angle Q is a right angle. We'd like to find PS. So first thing I'm going to do is I'm going to label everything that they give us, and I'm also going to draw one auxiliary line from point R to point P. In doing that, we'll create two triangles for us. A triangle on top, triangle RQP, and a triangle below, triangle RSP. Now, since angle Q is 90 degrees, it's a right angle, and this quadrilateral is inscribed within a circle, I know that angle S and angle Q will be supplementary. If angle Q is 90, there's no choice but for angle S to also equal 90 degrees. Well, at this point, I have two right triangles. And if I have two right triangles, I should be able to solve for missing sides. If I look at my top triangle, I have two sides and one missing side. If I look at my bottom triangle, triangle RSP, I have one known side and two missing sides. So I'm going to have to start with triangle RQP first. To solve for triangle RQP, I'm going to use Pythagorean's theorem, a squared plus b squared equals c squared, or 20 squared plus 15 squared equals y squared. 20 squared is 400, 15 squared is 225, 400 plus 225 will give us 625. Of course, the square root of 625, to get rid of that square, we need to take the square root, and the square root of 625 is 25 units. So therefore, y is equal to 25. And we needed to do that step because now that we have RP, well, now I have two sides of this other right triangle. And if I find the third side, well, that would be segment PS, which is what we're looking for. So again, I use Pythagorean's theorem. 7 squared plus x squared equals y squared. Y squared, of course, is 25, so I have 49 plus x squared equals 25 squared. 25 squared will give us 625, and 49 minus 625 minus 49 will leave us with 576. So x squared equals 576. From here, we need to get rid of the square, so we take the square root of both sides. That will leave us with x equals positive 24. So that means that PS is equal to 24. And with that, this problem has been solved. Our final problem of the day deals with a circumscribed circle here. So I have this quadrilateral XWYZ, or XWZY, I should say. And with this quadrilateral, this trapezoid, they're telling us, it is circumscribed about circle O. So again, I can see that it is going around circle O, so it's circumscribed. They tell us that angle X and angle Y are right angles. XW is 16, YZ is 7. We want to find the perimeter of this quadrilateral. So to get started, I draw in everything that's given to me. And as you can see, I'm putting congruency marks as well. The reason that these congruency marks go in is because these are all tangent segments. And I know tangent segments that share a common endpoint are congruent to the point of tangency. So each of these tiny tangent segments, these are all congruent to each other. Now, at this point, I notice that these on point X, on tangent line X, these both have one congruency mark. And the same can be said on tangent segments for point Y. They also have one congruency mark. The only reason I can do that is because they are both right angles. So therefore, they both need to go down far enough to still be tangent to the circle, but also have that 90-degree angle, which forces these tangent segments to all be congruent to each other. So let's go ahead and give these a variable. I'm going to go ahead and call them x. So one congruency mark is x. And of course, if these are x to the point of tangency, and same thing over here, then the full length would be x plus x, or 2x. At this point, this is a walk-around problem. So from point x to the point of tangency is little tiny x. That's that length. The full length is 16. So from point W to the point of tangency would be 16 minus x. If 16 minus x is on one side of our tangent segment, then it's also on the other. Because again, tangent segments that share a common endpoint are congruent. I'm going to go ahead and move over to this other side here for 7, for point Z. So I see that I have x from point Y to the point of tangency. The full length of YZ is 7. So from the point of tangency to Z is 7 minus x. Again, tangent segments that share a common endpoint are congruent, so they both get 7 minus x. At this point, we're going to add the tangent segments together. So I'm going to start at point Y and just walk around adding up all my segments. So therefore I have x plus x plus x plus 16 minus x plus 16 minus x plus 7 minus x plus 7 minus x plus x. From here we combine like terms. 16 plus 16 is 32. 7 plus 7 is 14. I have 4 green positive x's and 4 black negative x's. The positive 4x and the negative 4x cancel each other out, leaving us with 32 plus 14, which will give us a final answer for the perimeter of WXYZ being 46 units. And that is our final answer. Thank you guys so much for watching today. If you have any questions, please let me know.